Hi, everyone. This is Stefano Morani recording another podcast in relation to the Virginia Gas Project for Renergen. Renergen is a natural gas and helium company, dual listed on both the JSE and the ASX. And we recently announced an update by Sproul, which included Prospective resources for the first time. And I thought what I would do is that I would unpack the contents of the report in a more easily digestible fashion without all of the technical aspects to it. Everything that I'm going to speak about over here is already in the public domain in one form or another, and this isn't providing any forecasts on the company. This is just unpacking what we found. So again, like the Helionomics podcast, I'm going to share my screen vis-a-vis creating a whiteboard so that I can draw. And that way I can show everyone exactly what it is that we're talking about. So much like the oil and gas industry, the helium is also determined on a P, C, and U category in terms of your resources and your reserves. So just to explain what these are, you've got your proven reserves, and these reserves are what has been determined by the reservoir engineer as being commercially available. And these then have subcategories of P1, P2, and P3. And that's just the level of probability, basically. But it's the level of probability ascribed with your business plan in terms of the recoverability of what you're looking at pulling out the ground. But this has been determined as the gas is there, it's underground, and it's recoverable. You then get your contingent resources, and you'll get your C1, your C2, and your C3. And this classification of gas is, well, the gas is there. You just haven't put forward a business plan yet to show us how you're going to commercialize it. And until you do, these are going to remain resources. They're not going to remain reserves. We're not going to classify them as reserves. And then you've got your classification U, which is undiscovered. This is your prospective resource, and this is the report that we released recently. So the prospective resource really focuses on you've got sufficient evidence to show that this quantity of gas is there. We don't know yet whether it's commercially recoverable or not, and you haven't drilled and you haven't discovered it. But on a prospective basis, we'll give you recognition for the fact that the gas is possibly there. And that will also have its U1, U2, and U3 case. So now in our case, putting the methane aside, because I think everyone is familiar enough with the methane, we'll focus on the helium. If you take a look at our numbers and how these fit, I'm just going to bring up the latest presentation so that I can see. All right, so from a helium perspective, if we look at our proven helium, we've got 6.8 billion cubic feet of helium in the P category. You then add from the contingent side what the reservoir engineers believe is there. We just haven't proven its commercial recoverability yet. And this then adds on an additional 20.9 billion cubic feet. And then on top of that, there is the prospective resource, which is what we determined through the analysis with the University of Edinburgh and Sproul. You add on an extra 344 BCF, which would then bring the total to, let's just work that out quickly, 344, 20.9, and 6.8 puts us on a total of 300 and almost 72 BCF, which is just a ridiculous amount of helium. That'll be like someone gifting you a sand pit in the middle of the Sahara Desert. It's completely superfluous. So what does all of this mean? The world consumes per annum 6 billion cubic feet. Now, in dollar terms, the value of that, if we take a look at the 2018 BLM auction, so in 2018, the BLM auctioned helium at $286 per 1,000 cubic feet, which then implies that 1 billion cubic feet at that price is equivalent to $286 million, which is an awful lot of money when you consider how little gas that is relative to the amount of cash. It's significantly more valuable than, say, 1 billion cubic feet of natural gas would be. This puts the estimated annual value of the market of 6 billion cubic feet per annum somewhere between, well, somewhere in the region of about $1.8 to $2 billion upstream. And then obviously the mid and downstream where you start moving the helium into dewars, that's where you start to collect the additional profit margin. And there's obviously there's a lot that goes into that. So the total value of the helium market annually is somewhere between $3 and $5 billion. That's based on some estimates that we've seen. But for our purposes, we will stick to the upstream side of it, which is the large-scale production of bulk liquid helium. Now, when you consider how much we have in situ, you need to consider how much you're actually going to be capable of supplying and selling into the world. Now, very, very broad numbers. Before COVID struck, you had world consumption probably somewhere in the region of, let's call it plus minus 6 BCF per annum. After the falls in supplies for various reasons, I'm not going to go into that in this. I think that's easy enough to find in the marketplace. Give or take, supply was around 5 BCF, consumption was about 6 BCF, which left a shortfall of roughly 1 BCF per annum. And that is obviously where the big opportunity is being first to market in terms of being able to supply that gap. Now that gap is probably going to close out, and by 2024, 2025, that gap should all but be gone. So obviously first mover advantage is key in capturing that market. So how much of a resource is therefore really commercially available? And what's important is that if you're going to build a helium project, you need to know that you're going to be selling helium under contracts for probably a 10 to 15 year period. And if you're going to be selling for a 10 to 15 year period, then you need to know that you have sufficient helium to be able to cover that amount. Now, if you're looking to supply 1 BCF per annum, then all you really need is 15 BCF. And that will in essence cover you for a 15-year contract at 1 billion cubic feet. Your annual revenue from helium will be somewhere in the region of $250 to $300 million based on the prices that I'd indicated, and that would be the business case. Now, in terms of what the BCF, 1 BCF per annum translates to as a production capacity, your 1 BCF works out to 4.7 million tons per annum. And at 4.7 million tons per annum, using 345 days of production, you are looking at somewhere in the region of about 13.6 tons per day, which is an almighty amount of helium. So there's more than enough space for a few new entrants to come into the market to try and fill that shortfall. Where we are from, firstly, a resource perspective, just to recap, we had our P's at 6.8, and then we've got our C's, which is then additive, and that was, call it, roughly 21. So as it stands right now, we're already somewhere in the region of, let's call it, 28 BCF, plus minus. Obviously, what's going to be critical in our update is proving that this is actually commercially available to us in the P category. Not all of it, but substantially a large enough portion of it. Then you've got the U category, which comes in at 344 BCF. And obviously that number, I mean, just to put 344 BCF into context as to just what kind of a volume of helium that is, that would be something like $100 billion, if not more. It's an almighty amount of helium. It is really a very large volume of helium. Way too much for the world to ever be able to absorb if you're looking at these economics. Again, over the next 15 years, the world's probably only going to be able to absorb around 15 billion cubic feet worth of helium. So really anything over here just kind of becomes superfluous. But what is useful in the analysis over here is to know that if you have that quantity of helium as prospective by virtue of what's sitting underground, then your likelihood of being able to bolster this number and your likelihood of being able to convert these into those is a lot higher. And this is the encouraging thing about the report. This number is, I mean, it's anyone's guess as to what the true number is. So how did this report come about? Now, I've explained in various scenarios and presentations that we've got a resource which is characterized by the Karoo, which is about 300 meters thick. Then there's a thin dolerite cap. And then we've got a layer called the Wits. And then below that, there's a layer called the Dominion. Now, these two layers over here are extremely rich with uranium and thorium. Fortunately, given the high level of exploration that's taken place in this particular part of the world as a result of all of the gold, thanks to this asteroid, you've got a lot of data talking about the composition and the grades of uranium and thorium sitting in these layers. And so what we were capable of doing was taking a whole bunch of data from nearby mines and from the geosciences and from numerous other sources. And we were able to compile a relatively accurate list and map of exactly where the uranium and thorium is and the concentrations. In total, if memory serves, the geologists that worked on this for us, Shango Solutions, came up with a total value of uranium and thorium in place just within our production right, which is 187,000 hectares. They came up with a total value of somewhere in the region of 600 million tons of radioactive metal sitting just within our production right. What's more important is not only having the metal, but also having it there for a specific number of time. And the asteroid struck around 2 billion years ago, which means that this has been deposited and has been sitting underneath that cap for around 2 billion years. And that's important because uranium has a half-life of 4 billion years. In other words, it takes a very, very long time for uranium to break down into lead and to release your helium atoms. So time and pressure and radioactive metal are really what's key to the development of the helium. And so what would have happened is that you've got the uranium and thorium in here, and it will have been sprouting all of these helium atoms all over the place. And helium passes through pretty much everything. And so what happened in time is that all of this helium then migrated in the rocks and continues to do so today. And it finds its way into these faults and fissures that we have in order to find the path of least resistance up to the surface, into the atmosphere, and eventually into space. And so when we're drilling into these faults and fissures, and all that we're doing is that we're releasing this trapped helium that's been in there for billions, well, up to billions of years. And that's the entire thought process behind what went into us commissioning this report. What we needed to try and ascertain was just how many of these helium atoms have been produced in this rock, so that we know what the potential full extent of the resource is. And obviously the results showed some pretty spectacular numbers. But that also now speaks to why the concentrations are so high. So if you look at some of the higher concentrations in the world, the aggregate across the United States is around 0.35% concentration of helium in your gas on aggregate. That then goes down all the way through to Qatar, who, let me see why this isn't working. Qatar is recovering at around 0.0. It really depends on how their equipment is doing, but being generous, somewhere around 0.04. And this is again part of the fact that they've got uranium sitting underground. It's in a very large gas field. It's been there for a really long time, and it's produced helium as a byproduct of radioactive decay. The big differing thing between these fields and our fields is just the high levels of concentration of uranium in the area. So there are parts of the Dominion, which I referred to earlier, where there are concentrations, there are little pockets of concentration of 10 kilograms per ton of uranium sitting in the rock, which is a very, very high concentration of uranium. Normally you're talking about 3 to 5 grams, not kilograms per ton. Here you've got concentrations of uranium and thorium in certain pockets, which have managed to clock up to 10 kilograms per ton. And that is really the genesis of why our concentrations are so different and why there is so much helium. So what this prompted us to do was to commission, once we got the data back on uranium from Shango, we then went to the University of Edinburgh, and we had our experts then quantify the amount of helium that would have been produced within our production right over the area, which they did, and they obviously came up with their original figures, and then that was given to Sproul, who then used completely accepted methods in the oil and gas industry to be able to quantify a range as to how much helium has remained behind within the field. And that gives the U1 to U3, which is obviously plus minus the 30 BCF all the way up to the 344 BCF. Again, this is all fairly academic. Do we have $100 billion worth of helium in the field? Look, it's not really. That's again another academic question, because even if all of that helium were actually there, would we be able to recover it? Chances are no, we would not be able to, because we wouldn't be able to sell it. Are we very confident about us having at least 20 to 30 billion cubic feet worth of helium sitting underground? Well, at this point, given the fact that the contingent resources alone added up with our proven reserves, already is very close to the 30 billion cubic feet mark. We're relatively confident that that we'll be able to recover that volume of helium. How much do we need in order to build a world-class project? Yeah, at present, anything over 20 billion cubic feet is already a waste. Comes back to that analogy of the sandpit in the Sahara. It's kind of completely superfluous. So yeah, we're obviously doing all of our work, and in September, hopefully, we'll be able to update the market with what we've managed to put together and prove to the reservoir engineers what is recoverable and what our business plan is on selling it. But I think the key message over here and the important thing is to help everyone quantify exactly what the size of the market is, which I hope to have achieved in the earlier part of this podcast, as well as what the slice of the pie is that Renergen is now aiming for. So again, this is not a forecast. This is a hope until we actually get the results back from Sproul later this year. We won't have a definitive answer yet, but it's certainly our intention to try and build a helium liquefier for the second phase and have that come online, ideally, in an ideal scenario, sometime around 2023. And that would be a liquefier, if all things go according to plan, somewhere around 5 to 10 tons per day. So now just doing the maths and converting that back into cubic feet. So 5 tons per day on 345 day per year cycle for production. It's going to give you about 1.7 million kilograms per annum, which in cubic feet is, call it just shy of 400 million cubic feet per annum. So the range on the kind of liquefier that we're hoping to install for second phase will be somewhere between 400 million and 800 million cubic feet of helium per annum. So at the very least, if we wanted to do 800 million cubic feet per annum for, say, the remaining life of the field to 2042, that would mean that we would need somewhere in the region of 16 BCF, which we're already comfortably within that space. If you look at the P's and the C's. Now, obviously, it's just a case of showing that it's commercially viable to extract the C's, which, given the current pricing of helium and the low cost of drilling in our field, we're, as management, we're relatively confident that that isn't going to be an enormously difficult task to achieve. I hope this has been insightful. This was obviously also based on some of the questions that we've received from some shareholders. So this was just summarizing all of the publicly available information in one neat spot where you didn't have to read through everything, and hopefully my chicken scribbles on the whiteboard were useful. So thank you very much. Keep the questions coming, and we will be in touch soon. Thank you.